And I'm on page 27 in the unit guide.
Mister, what do we staple our homework to? If we get it on a separate sheet?
Oh, if you get it all on one piece of paper, then there's no need for a staple, right? Just put it in the middle of the table. Okay, are we good?
Yeah.
Can we all get back to my favorite lesson ever?
Yeah.
Mind-blowing. There will be thunderous applause at the end of the period. There might even be some crying in the middle, but at the end there will be applause because it's that good. All right, Karina is ready. Oh, no. Okay, Michelle's back. Karina's ready. Everybody good?
Yes, sir.
All right, so for the last, oh, I like that. For the last couple of lessons, we have been looking at this guy, the definite integral. Right? Definite integral means, what does it mean again? When you see definite integral, you know I'm asking the question, area, bounded by four things.
The graph,
The graph,
the x-axis,
the x-axis,
the line, the interval,
the line x equals a,
and the line x.
and the line x equals b. Okay? And what are the ways that we've used to find the exact area?
That point method.
We've got the left endpoint method, the right endpoint method, the midpoint method, and we get the trapezoid method, and you guys have been getting practice in class and outside of class, and hopefully the methods themselves are really comfortable. But here's the thing, I asked the question, how can you get the exact area? And what you all just named off, left endpoint method, right endpoint method, midpoint method, trapezoid method, those aren't giving you exact areas, they're giving you estimates. Are we okay? Sometimes an overestimate, sometimes an underestimate. They're giving you estimates. Riemann, God rest his soul, was able to take the idea of these estimates and move it from an estimate to the exact area. And that is really like why we still study the work that he does. It is going to completely change the course of AP Calculus and the work that we do. And I'm really excited. And we're doing some of it today. Good times. All right. So for those of you in the cheap seats, or maybe you were out that day or you get hit in the head by a rock on the way to school today, we've got a graph. Is everybody okay? We've got Paul in the back. Take a look at this graph. What method are we using?
Right. No, left.
Look at the graph.
Left.
Look at those rectangles. Each of these rectangles, Chris, you seem pretty confident that this is the left method, the left endpoint method. How do you know it's the left endpoint method? Wait, because what?
You have extra.
That's not why. How do you know it's the left endpoint method? Because you're starting on the left, but the thing is, the height of the rectangle is determined by the left side. Are we okay? We've done this before. Overestimate or underestimate? Overestimate. Now here's the thing. You are all looking at the graph and you know it's an overestimate. Jeanette, what is it that you're seeing about the graph that says clearly overestimate?
The rectangles are outside of the function.
The rectangles are outside of the function is one way that you could say it. I like it. I don't 100% love it. It wouldn't get you all the points. Rebecca?
Can you say that the height it goes up to the curve? And then
The height goes up to the curve.
when you say the left point, the left increment you go up to the curve for each of the.
And what happens when you use the left and you go up to the curve and you go over and you go down? What happens with the amount of area that you're capturing? You're capturing more area than what you need to? Here's the thing. When you explain overestimate or underestimate, you have to tell me two things. Name the method and tell me what the function's doing. What's this function doing?
Decreasing.
This function, is that okay? We're decreasing? You have a decreasing function. You're using the left endpoint method, so you have to get an overestimate. Are we good? I'm curious, I want to get some hands on this. How would you make the estimate better?
More squares.
That's so funny. I thought I said, can I get some hands on this? And Jackie is like, oh. Hi, Jackie. What would you do?
More rectangles.
More rectangles. How many more would you like?
7.
7. You'd like 7. Okay, Paul, let's make it 7. So double click on 4 and make it 7. And we get more rectangles. And we get a more accurate answer? That's a better answer. Can anybody get me a better answer? A better estimate? Jose?
100.
100. You want 100 rectangles. Double click, let's see what happens. 100 rectangles. Wow, look at that. So many rectangles, I can't even see the error anymore. But is there error?
Yes.
Right, we know because we're looking at this. Riemann did his work in the 1860s. There was no geometry sketch pad. There was nothing for him to look at. There was no tech. He did this without tech. 100 rectangles is good. I want better. I want better. How about 1,000 rectangles? Paul, can we do 1,000 rectangles or is it going to blow up? I'm not sure. 1,000. Even at 1,000, look at this, not exact. Still some error. How would we go to the exact right answer? We've looked at 4, 7, 10, 100, 1,000. How many rectangles is it going to take to get to the exact area? There's no more error. How many rectangles is it going to take? It's going to take an infinite number of rectangles. I'm mind blown already. We've been playing around with finite numbers, 4, maybe 5, maybe 6. Today we lay the groundwork to go from this finite number to the infinite. We okay? All right, good. We can navigate away from that. I need you guys, so let's turn the lights back on. You guys need to take out your calculators, and we're going to go to page 27. Wait. Paul, don't go too far though. All right. All right, Daisy, can I get you to read over here about our friend Riemann?
Our friend Riemann did not have access to
Okay, hold on. There's some conversations going on out there. I'm not sure why.
That's not on page 27 for us. Oh,
That's
yeah,
not-
it is on, like,
You exist. All the thoughts coming through the brain, out the mouth today. Okay, 27. Take it away.
Our friend Riemann did not have access to a fancy graphing calculator, nor did he have geometry sketchpad available to determine the exact value of a definite integral. However, he did have access to a amazingly flexible mind and other historically significant
Mathematicians.
mathematicians. His professor Carl
Friedrich Gauss.
Jacobi
Dirichlet.
and even Einstein. It's time to continue down the road with Riemann to see how he really determined the exact value of nice definite integral.
Okay, so over here at the right, we've got a parabola. This is a very nice, I have to choose my functions wisely here if we're going to do this without your brains exploding here. All right, so we've got some parabola over here. Using your graphing calculator, find the exact value of the definite integral from 0 to 3 of f of x dx. I would hope this is like quick and easy. Everybody knows what to do. I've given you a function. I want you to find the definite integral. Do that. Once you've done part A, call me on over and I want to move you over to part B. You've got 5 minutes working in your groups. You get your calculator, see what you can do. I'm going to be a proud papa. Perfect. Keep going. What are we getting for answer? 39. Where's the rest of them? 106. So is that one that we're going to turn into tomorrow? Okay, hold on. 39 pages. Don't. Okay, keep going.
We put the equation and then with this B, plug in the
I need to underestimate.
What'd you get for your 39? Okay, good. 39, keep going. Okay, at this point, just about everybody seems to be convinced there are 39 rectangles. Sorry, not 39 rectangles. The area is 39. Keep going. Using 8 rectangles of equal width and the right endpoint method, estimate the value of the integral from 0 to 3. Before you determine the final value, will this method give you an underestimate or an overestimate? How many guys are going for an underestimate here? How many guys think we're going to have an overestimate? How many of y'all have no idea what's about to happen? Yep. If you look at this graph, on the interval 0 to 3, in which method? Right endpoint method. Use the right endpoint method. Overestimate or underestimate? Imagine those rectangles. That right endpoint method. Every time you make a rectangle, you use the right side, go up, over, down. So you're going to get an overestimate because the function is increasing and you're using the right endpoint method. So overestimate because right endpoint method and increasing function. All right. For the folks that need a little bit of a nudge here comes the nudge. I want 8 rectangles. They all have the same width. That's going to be really important for the work that we're doing. You're trying to go from 0 to 3 using 8 rectangles of equal width. How wide's each rectangle?
3/8.
Depending on your preference, you might speak decimal and say 0.375. You might speak fraction, and in fraction you're going to say 3 over 8. So delta x is 3 minus 0 over 8, 3/8. The 3/8 is the width of each rectangle. So now I've got to think about, and I'm not even going to try getting in this little space. If I'm going to go from 0 to 3, and each rectangle has a width of 3/8, where are my cut points? The first rectangle starts at 0, where does it end? At 3 over 8. How about the next one? 3/4 if you reduce it. Let's avoid reducing.
6/8.
6/8. Next one?
9/8.
9/8. Next one?
12/8.
12. 15/8. 18/8. 21/8. The last one would be 24/8. Good news. That's 3. These are your cut points. This is the partition. When I make that first rectangle, think about that first rectangle when I try to find the integral. To find the area for the first rectangle, I need the width and I need the height. How wide? Oh, this should be the easy question. How wide is the rectangle? 3/8. That's what we just decided over here. So it's 3 over 8. How tall is it?
F of 3.
Right. 3/8 is the endpoint. How tall? It's what you get when you plug 3/8 into the function f. So it's 3/8 times f of 3/8 is the first rectangle. Okay. That's your first one. Second rectangle, I go to that other endpoint, up, over, down. How wide? How tall?
6/8.
How wide is the rectangle? 3/8. They're all 3/8 in width. How tall? Right, where is the endpoint? It's at 6 over 8, so this is f of 6 over 8. That's the first rectangle. Here's the second one. Third rectangle. How wide, how tall?
3/8.
3/8.
9/8.
F of 9/8, not 9/8. F of 9/8. Okay, Rebecca.
Since you multiply by the f of the function times 3 of 8, can
Yep.
you just like, distribute out the 3/8?
Factor out the 3/8, right? We can factor out the 3/8 if we want to, because they all have the same width. Right, I think some of you guys are making progress here. So the next rectangle is 3/8 times f of 12/8. 3/8 times f of 15/8. 3/8 times f of 18/8. 3/8 times f of 21/8. 3/8 times f of 24/8. Did we capture all 8 rectangles?
Yes.
So the only thing left for you to do is type this in the calculator and get an answer. Okay, take a minute, get that done. If you haven't already typed in the function as f, like f1 on your calculator, you're going to want to do that now.
Mr. a question.
Yeah.
I thought for the right point method, you don't include the last number.
No. You do include the last number. Because as you're making your rectangles, Karina, you always use the right endpoint. Oops. Right, up, over, down. Right, up, over, down.
So you don't include the first one.
With the right endpoint method, you don't include the first one, but you do include the last one. With the left endpoint method, you include the first one, but you don't include the last one. Okay. So at this point, you're just typing all this into the calculator. Some of you are probably already asking the question, why, God, why do I have to type all this into my calculator? Riemann didn't have a calculator. You're right. There has to be something more. And we're going for the more. Jeanette, you doing okay? Okay. Some people, I saw 25.67 something as the answer. That has got to be the wrong answer. Why does 25.76 whatever have to be the wrong answer? We know we have to get an overestimate. We know the true area is 39. This cannot be 25 anything. I saw 43 something, 44 something. When I did my calculations, I've got 44.765. 44.765. Honest hands here. How many guys honestly got 44.765? Okay, good. I can deal with that. Time for a push. If you can do 8 rectangles, could you do 20?
Yeah.
It's going to take a little longer, but you could do 20. Could you do 50?
Yes.
Could you do 100? Could you generalize this to any number of rectangles? This is what Riemann did. And so there you're going to flip over a little bit. Okay? It's all good. You're going to be fine. What we're going to do is we're going to repeat this process. It's going to feel similar, but it's also going to feel pretty different. And I think some of you are going to freak out on me. Don't freak out on me. Do not freak out on me. You're in good hands. All right. Same problem. Same function, same interval, but this time, how many rectangles? N rectangles. The very top of the next page. I want to do this with N rectangles. And I think some people are going to get a little uncomfortable because you're like, well, what's N? N is any number I want it to be. Jose wants 100 rectangles, make it 100 rectangles. Somebody wants 1,000 rectangles, make it 1,000 rectangles. N is whatever number you want it to be. Yeah?
Wait, can't you just do 3/8 times, like for the last problem, since
Yep.
there was 8 rectangles, couldn't you do like 3/8, let's say it was like the second rectangle, can't you do 3/8 times 2?
Okay, hold that thought for a little bit. Because you're focusing on the 8. I want to go from 0 to 3. How many rectangles? N rectangles of equal width. So my question is, How wide's each rectangle?
And
Mm-mm. It's not n.
Oh, this 3 over n.
When there were 8 rectangles, we had to take the width of the interval, how wide was the interval, and divide it by the 8. So in this case, how wide?
3 over n.
It's going to be 3 over n is how wide each rectangle is. Already it's a little abstract. Well, if I'm going to go from 0 to 3, well, tell me about that first rectangle. That first rectangle has a width of 3 over n. It starts at 0. Where does it end?
3n.
3n.
Not 3n.
1n.
Not 1n. 3 over n. Yes, I'm that picky. You have a width of 3 over n. You're starting at 0, add 3 over n. Where does the next rectangle end? 2 times that, right? 6 over n. How about the next rectangle?
9 over n.
9 over n. The next one?
12 over n.
12 over n. The last one?
N over n.
Not n over n.
3 over n.
Not 15 over n. Where should you best be ending?
1.
Where are you supposed to end?
3.
3. I lost some folks here. Each rectangle has a width of 3 over n. How many rectangles does it take to get to the last part? Each rectangle has a width of 3 over n. 3 over n. 3 over n. 3 over n. How many times do I move 3 over n? You move n times. And 3 over n times n is 3. Exactly where I want it to be. That's your partition. When we do the rectangles, it's the right endpoint method. So I go up, over, down. Up, over, down. Up, over, down. Up, over, down. And I just keep on going. Well, what's that integral? Take a minute, talk to somebody near you. What's the area for the first rectangle? How do you find the area for that very first rectangle? Don't talk to me, talk to folks near you. Area of a rectangle, you know how to do this. Area is base times height. Length times width. So for that first rectangle, how long is the base?
3 over n.
3 over n. How tall is it?
F 3 over n.
Be careful, which method? Right endpoint. So you use the right point, you go up to the curve to determine the y value. So your area is 3 over n times f of 3 over n. That's your first rectangle. I want to get some hands in this. What's the area for the second rectangle? Jackie, don't call it out. Area for the second rectangle. The first one was 3 over n times f of 3 over n. Rebecca, what do you got?
3 over n.
Yeah.
Times f of 6.
3 over n times f of 6 over n. Love it. The width is 3 over n. The height is determined at the right point, so f of 6 over n. Henry, what about the third rectangle?
3 over n times f of 9 over n.
3 over n times f of 9 over n. Love it. The base times the height. Daisy, tell me about that fourth rectangle. How wide, how tall?
3 over n times f of 12 over n.
3 over n times f of 12 over n. Love it. Diego, tell me about that fifth rectangle.
3 over n times f of 15 over n.
F of 15 over n. And that's the fifth rectangle. And we keep on going. And we're going to do dot, 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 until you get to the last rectangle. Axel, how are you feeling about this last rectangle? How wide, how tall? Wait, what? The width? Stop saying 3n. 3n means 3 times n. You mean 3 divided by n? Times that last rectangle, this very last guy here. Not f of n.
F of 3.
F of 3, or I'm going to write it this way, is f of 3 over n times n. Everybody okay? Anybody seeing a pattern yet?
Yeah.
So did Riemann. Riemann saw a pattern, Annie had some notation to be helpful here. Here's what he did. All of this, we're adding, we're adding, we're adding, we're adding, we're adding. You have a notation that you haven't used for a while that means add it all up. You learned it in sequences, you've used it in physics class. Big sigma?
Oh, yeah.
Sigma means add.
The sum.
Right, now you would say like the sum of the forces in physics class.
Yeah.
What we're adding here is we're adding areas. Now how this is going to work is a little bit different. What we did in pre-calc is you would have had like an index, you had a counter. And so I'm going to start my counter at 1. Now, what we're looking for is a pattern in these area expressions. Anybody see any patterns? Henry, what's a pattern that you see?
Each one's getting multiplied by 3 over n.
Every one gets multiplied by 3 over n. You're frozen for a little bit. Anybody else see a pattern? Any other patterns in these area expressions? Marilyn, what do you see?
The numerator of f of times.
Okay, we're doing f of something. I want to freeze you right there. All of them are f of something. What other patterns? What's the same in every single thing? Destiny, what you got? The width, that's the 3 over n. We're doing f of something. Karina, what do you see?
We keep adding 3 over n.
You keep adding 3 over n. Paul, what else? They're all what? Not factors. Wrong word there. Multiples of 3. They're all multiples of 3. They also all have a denominator of n. Right? We're dividing by n our number of rectangles. Paul just said the numerators are multiples of 3. The way that we're going to write a multiple of 3 is we're going to say 3 times I. 3 times your counter. Stay with me on this. If I is equal to 1, your first one is 3 over n times f of 3 over n. Did that work?
Yeah.
The way your counter works is it grows by 1 every single time. So you started at 1 and the next one? 2. Try 2. 3 over n times f of 3 times 2. Oh, 6 over n. I is now equal to 3. 3 over n times f of 3 times 3 over n. Oh, it worked. When do I stop? When do you stop? You stop at
8.
n. Not 8. It used to be 8, now it's n for any number of rectangles. So where we are now is that our integral is approximately going to be represented by big sigma. This is a new idea for us. And here comes a new calculator skill. It's going to be good. All right, Paul, I need you to switch over to the TI Inspire. Everybody else needs to take out their calculator. Paul, if you could increase the size a little bit. How what?
So you know how in the last one we kept going up by 3/8 because it was with 8 rectangles?
Because there were 8 rectangles.
Well, how come this time we also went up by 8?
No, I didn't go up by 8. We went up by 3 over n. Paul, can you hit the plus sign down here to grow? So the integral right now, the integral from 0 to 3 of f of x dx is approximately what we're getting here. F of 3i over n. Okay, so here comes some new skills. Part D. Using what you know about sigma notation, we can simplify this a little bit more. We're moving over to E. I want 120 rectangles. 120 rectangles. How wide would each rectangle have to be?
3 over n.
Be specific. Either 120 rectangles. How wide is each rectangle? Not 120 over 3.
1 over 40.
1 over 40 is the same as 3 over 120? Each one has a width of 120. We are not going to go and draw 120 rectangles. I don't have time for that. But what I know is that n is 120. So when I do my sigma notation, I goes from 1 to 120. How wide is each rectangle going to be? 3 over 120. How do I find the height of each rectangle? It's f of 3 times your counter, 3 times I, divided by n, 120. So, here comes the new calculator skill. Paul, we can delete all that good stuff out of there. There we go. And we're on the calculate screen. I want you to find your templates button. Find that templates button. It's the one near the Bible. Anybody see anything here that's going to be helpful?
Oh, yeah.
Oh, yeah, the little.
The little, not E, sigma. Sigma. Where is it?
It's like on the second row.
Second row, right over here. Click on the template. Magic is about to happen. Does everybody know what to do with the template?
Put 20 on the top.
You're going to fill in all the boxes. Okay? Now, you can use I if you want to. You don't have to. You can call it X, you call it T, you call it G, doesn't matter. Okay? The one thing though, Paul, on the graph, did you type in the function? You did? Perfect. You have to have identified the right function for this to work. Okay, so Paul, go up to F1. Oh God, Paul. Let's delete all that nastiness out of there. And what's it supposed to be? 2x squared plus 4x plus 1?
Yes, sir.
Okay. So 2x squared plus 4x plus 1. 4x plus 1. Enter. There's your graph. Go back to your calculate screen, fill in all the things. 3 over 120 times f of
At the bottom, you put F or something.
times now it's f1. Good. Open parentheses and then 3i over 120. So you're getting an exact answer out of your calculator. Okay. In order to make this work, you have to have on your graph screen typed in f1 is that 2x squared plus 4x plus 1. And according to Paul's calculations, 39.376. How many of you guys are getting 39.376? Does 39.376 even make sense for this problem?
Yes.
Does this make sense?
No.
I don't know.
Oh, kind of.
We really don't know.
Last time we had like 44 and some change. We increased the number of rectangles, which increases the accuracy. And now we've got 39.376. Does this make sense?
Yes.
Still an overestimate. Getting closer to 39. Use your newfound calculator skills. See if you can get closer. See if you can get closer. Yeah, keep going. You get 39.376. Perfect. So your calculator give you an exact answer first. Okay, just fix it. Okay. Part F, 1,000 rectangles. With 1,000 rectangles, each one has a width of 3 over 1,000. And then I evaluate f of 3i over 1,000 from 1 to 1,000. Is the answer going to be bigger than 39 or less than 39? No matter what you do, you have an increasing function and the right endpoint method, you have to get an overestimate. You have to. But it better be closer. Okay. Daisy, what are you getting on your calculator?
I got 39.45.
39.045. Anybody else get 39.045? Okay, we get some folks getting 39.045. Your calculator's doing all the heavy lifting here. All the heavy lifting is being done. But here's the thing. I think part G asks you to go to 10,000 rectangles. Go to 10,000 rectangles.
They go my calculator.
10,000 rectangles. That's going to be the sum from 1 to 10,000. 3 divided by 10,000. F of 3i divided by 10,000. Still going to be bigger than 39.
39.005.
39.0045. 39.0045. All the friends are okay? We have about 7 minutes left. This is where I need to be. Here's the thing. You just calculated the area using 10,000 rectangles. How long would this have taken Riemann?
10,000.
Probably forever, because he didn't have a nice graphing calculator to plug in all of the stuff and say, oh, magic calculator, do the work for me. He didn't do that. And even if he did have that, is anyone going to tell me that 39.0045 is the exact area?
No.
This is still an estimate. I want to get better. I want to get exact. How do we get exact? How do we get the exact area, not an estimate?
Do we equal it to a number and we have to find n?
That's an interesting idea. So you would set this whole sigma notation equal to 39 and then try to solve for n. That's an idea. You could play around with that for a little bit. What has to happen to get the exact area? We talked about this a little while ago. The number of rectangles keeps increasing. To what? To like 100,000? Even at 100,000, it's an estimate. At 1,000,000, it's an estimate. How do you get past having an estimate and get to the exact value? You need an infinite number of rectangles. So to get the exact area, so this is where we're going. If I want to do the integral from 0 to 3 of f of x dx and not approximate but get an equality, what I need to do is I need to say, okay, so let's do this sum from 1 to n of 3 over n, f of 3i over n. But I need an infinite number of rectangles. And so you might say, oh, well, just let n be infinity. And Calculus BC student, Roberto, we're going to spend a month, you're going to spend a month by yourself studying infinite sums. It's going to be a beautiful experience. You're going to absolutely love it. Love, love, love it. That's a Calculus 2 topic for all of you who are going to take that next year. To get the exact answer, you need an infinite number of rectangles. So some of you might be thinking, oh, I know what to do. I'll just type this in on my calculator.
Yeah.
Yeah, go find the infinity button.
Is there even one?
There isn't one. There's no infinity button. But here's what I care about. Are we okay with this idea that to get the exact area, we need an infinite number? Did you just find the infinity button? Okay, but if you try plugging it in, it does nothing. To get exact, we need infinity. So here's the part where it's going to be a little bit waving of the hands. I'm going to write it this way. The limit as n approaches infinity of the sum from 1 to n, 3 over n, f of 3i over n. Paul, you're done back there. But thank you for your service to our class. Unfortunately, our pre-calculus curriculum does not actually do what I would need to do here. There are some properties of sigma notation. I just need to move this out of the way. Sorry, I get so excited. I just get so darn excited here. There are some properties of sigma notation that you're not even aware that they exist. That's going to allow us to rewrite this expression. And we're going to write it as limit n approaches infinity of this sum from 1 to n, 3 over n, f of 3i over n. F was what? 2x squared plus 4x plus 1? Is going to be 2 times 3i over n squared plus 4 times 3i over n plus 1. All I did, f, we knew f was 2x squared plus 4x plus 1. So for me to find f of 3i over n, all I did is everywhere there was an x, I plugged in 3i over n. Here's the part that is going to seem foreign, that you wouldn't know this. This whole expression over here is equal to 9 times n plus 1 times 2n plus 1 over n squared plus 18 n plus 1 over n plus 3. If in your notes you just want to say a miracle happens, that's fine. It is not what I'm focusing on. How do you go from here to here? I don't need anybody in the class to worry about that. Not even the BC students need to worry about how do you go from here to here. Okay. What we need to do in this last minute, 2 minutes, what's that limit? What happens as n approaches infinity? You've got 9 times n plus 1 times 2n plus 1, and if you were to multiply all that out, you're going to get something with an n squared, right? What's the coefficient? 9 times n times 2n. Is that 18? You're going to get 18n squared plus some stuff? And an n squared in the denominator. You all know what that limit is. Not infinity. 18n squared plus some stuff. Because it's 9 times n times 2n divided by n squared. 18n squared in the top, n squared in the denominator. Take the limit as n approaches infinity. What happens? 18. Plus what happens over here? 18 times n plus 1, you get 18n plus some stuff with an n in the bottom. What's that limit? 18 plus the limit over here? 3. 18 plus 18 plus 3? 39. Insert the thunderous applause here. No. Thunderous applause. Thank you. Not weak sauce applause. Not weak sauce applause. So we've got some new calculator skills. We've got, finally, we left like baby land of 4 rectangles, and we've gone to like the infinite case. We're going to play around with this again tomorrow. Tonight's homework, 3 response corrections, get them done. See you later.
This is when you had to memorize those n equations?
No. That is not part of Calc AB or even BC. I did it with BC too. The problem is, we don't do it in pre-calculus enough. I'd have to spend a week, or maybe like 2 lessons, to teach you just the skills to go from here to here. And I don't care about that. Diego.
How long do you think it took Riemann to figure out that he can just
I think it took him a lifetime.